Hi everyone, I'm Daniele Paletti, a Master of Science student in Computer Science and Engineering at Politecnico di Milano. Today we are talking about Dovado, an open source design space exploration framework. Let's start by talking about the notion of design space we will employ throughout the presentation. RTL parameterization enables the generation of highly customizable modules and the birth of system-on-chip generators. For instance, in VHDL, we refer to parameters as generics, while in Verilog or System Verilog, we simply declare them as parameters. Many other emergent HDLs are nowadays tackling the problem of module parameterization. We then define the design space as the space of permutations of module parameters. From this definition, we can already see that the dimensionality of such space is factorial in the number of parameters. Thus, its volume, it makes it unfeasible to do manual exploration. On top of this, exploration requires synthesizing or implementing every design point we want to analyze. This makes the exploration even harder. So now let's talk about the problem and how it has been explored in literature. Hammerquist and other authors define the search problem as a search among architectural features. Such search is harder than the one we defined because it requires a greater parsing efforts that requires, on top of parsing the declaration section, also the parsing of other sections of the code. Karakaya and other authors treated this problem as a single target optimization problem by defining a power delay area product to optimize, thus reducing the complexity of the optimization problem. Such simplification, however, greatly harms the descriptive power of the optimization matrix, which cannot account for the occupation of different sections of the device under inspection. Pilato and other authors extended the mathematical treatment of the design space exploration problem to a multi-objective optimization problem, and proposed the use of the NSGA2 algorithm for its solution, thus significantly informing the approach we offer with Dovado. On the other hand, there are visual performance models, which tackle the same problem but from a completely different standpoint. Many approaches have been explored in the literature, such as Locka and Roofline, which you can see an example in the slide. Dovado, in this scenario, fits as an open source design automation tool that employs existing hardware design suites to ease design point evaluation and, consequently, design space exploration. Dovado's implementation is pure Python, and it is easily installable from pip as a command line tool. This means that it can be easily introduced in any existing pipeline. A pure Python implementation also eases the process of contribution to the Dovado codebase. Its modular design, in fact, allows adding support for any HDL of choice just by building a parser for the declaration sections. It is also easy to add support for any physical tool other than the ones already supported. Now, let's take a brief look at the main components of Dovado. We will proceed top-down from inputs to outputs. In the first place, the designer needs to specify the optimization metrics, the board, and the RTL design. Generally speaking, all the metrics computed from the physical tool are available to the user as usage metrics, while the maximum frequency is computed from the worst negative slack. The RTL design is then processed through two steps, parsing and boxing, which we will discuss further briefly. Then Dovado generates the scripts for the physical tool. Such scripts are TCL scripts in the case of Dovado, which are customized at runtime. Before going on with the description of Dovado's main components, it is important to understand in what way Dovado may be seen as a design automation tool. The design automation feature of Dovado works by taking as input an RTL hierarchy. The hardware developer then specifies a set of design points to implement or synthesize. Eventually, the developer may also specify directives to pass to the physical tool. The tool outputs the maximum achievable frequency together with all the chosen usage metrics. We are now ready to dive deeper into Dovado's main components to get a clear idea of how Dovado achieves design automation and design space exploration. The first step that the input RTL undergoes is parsing. VHDL, Verilog, and System Verilog are context-free languages. Thus, a context-free parser takes care of the parsing section. The declaration section of these languages is, in principle, a regular sublanguage, but the many concurrent standards make it very hard to use regular parser for parsing subsections. After the RTL module has been parsed, we can pass to the boxing section. The boxing section creates a box module that encloses the module to be analyzed to avoid pin overflow and undesired simplifications. These operations are carried out with VHDL and System Verilog boxes, which are parameterized at runtime to connect to the correct ports. The box component is now ready to be either synthesized or implemented on the target port. As of today, Dovado supports Vivado as a synthesis and implementation tool. So, to interact with Vivado, as we said earlier, we use TCL scripts, which customize at runtime with relevant information about the module under inspection and all the directives which the user may choose. On top of the design automation feature, Dovado builds design space exploration. We handle the design space exploration problem as a multi-objective integer optimization problem. We say multi-objective because the usage metrics together with the maximum achievable frequency are the objectives to be optimized. Integer because in VHDL and Verilog and System Verilog, non-integer parameters are not synthesizable. Such an optimization procedure is very expensive to carry out. We thus take advantage of the incremental design flow that Vivado provides. Vivado allows running multiple synthesis and implementation under the incremental design flow, so that at every run, only the sections of the design which are changed upfront with the parameter change are either resynthesized or re-implemented. This yields some computational advantages, but we also devised a fitness function approximation model to lower the number of calls to Vivado. The fitness function that the genetic algorithm optimizes is, loosely speaking, a call to Vivado. which either synthesizes or implements the desired design. Such code is computationally expensive. We thus used an approximation model trained in a supervised manner online with the points computed by Dovado. We have the trained data comprised of the points that the algorithm requests to Dovado and the target data as the output of the Dovado computation. A controller decides whether to call the estimation model or the real model based on the distance of the current design point from the points already analyzed. After getting a gist of how Dovado works, we will see it in action on several real-world examples. Let's start by talking about the experimental setup. All designs were targeting 1 GHz as a maximum achievable frequency. We used PyMu as the implementation for the NSJ2 algorithm. Antler was used for parsing VHDL, Verilog, and system Verilog with the grammars available in the repositories. As a physical tool, Dovado 2019.2 was used. We first tested the approximation model on a RISC-V implementation, and we found that the MSE, mean squared error, was effectively decreasing with an increasing number of samples. This means that the approach of fitness function approximation has further space for analysis, but we decided not to use it for other tests, and instead we stuck to only using Dovado. Here, now, we explored the design space of Tyrex, a VHDL domain-specific architecture for regular expressions. We used 4 parameters, you can see here, and constrained their values to only be in power of 2s, which is another constraint that can be user-defined for each parameter independently. As metrics, we used LUT and register occupation together with the maximum achievable frequency. As you can see here, 4 solutions, non-dominated solutions, were found. At this point, we run the same experiment on a larger board. And as expected, the number of non-dominated solutions grows. We now decided to move from VHDL to pure Verilog with Corundum. If in the case of Tyrex, the result shown regarded only the top module, in the case of Corundum, we decided to use a non-top module, in particular the Q-handler module. In this case, we had LUT occupation, register occupation, BRAM occupation, and maximum achievable frequencies as metrics. As we can see here from the plots, the register occupations and the LUT occupations vary widely among solutions, while BRAM occupation is not affected at all from parameter change. We can also see that the maximum achievable frequencies does not vary much. Now, as a closing example, we have a VHDL RISC-V core. Here we used the same metrics as before. And we can see that in this case, also the BRAM occupation is affected by the parameters chosen. In particular, we can see from the BRAM plot that solution E has a BRAM occupation of 4%, while solution A has a BRAM occupation of 14%, thus inducing a significant change. Concluding, Dovado is a modular system, and it ensures flexibility in target devices and HDLs, both for synthesis and implementation. On top of this, Dovado also provides a model for approximating synthesis and implementation through an estimation model that is trained incrementally. However, further work needs to be done. This parser can be improved to support many more HDLs. The approximation model and the control model in particular must be further studied to provide significant runtime improvements without sacrificing too much accuracy. And also, visual performance models could be beneficial for having a clear vision of the area frequency trade-off. Thank you for your attention. Bye.